All right, I'm trying OBS today, just messing around with it, hoping that we don't have audio issues like we do a lot of times. Sometimes you get a software update that might fix the problem. And not quite sure right now why my chat box was where it was, but I'm going to move that over just a bit and see if I can do a little hangout on the sun today. So, short notice and all, but I thought I should do this. There's a sundial here on the screen you can see, and what that says is that we can know the sun's azimuth in the sky by which way the shadows go. And just to give some terminology, if you don't know, that thing on the top of the sundial, it's called a gnomon. I think that's how you pronounce it. And the sun is obviously the opposite direction. You point this thing toward true north, not magnetic north. True north is basically Polaris in the northern hemisphere, or whatever you want to call it. So it's pointing at Polaris, which is nice because if you have it permanently mounted, your sundial, even at night, if you go out and you want to line up with Polaris instead of magnetic north, you can just shine a flashlight on your sundial and see which way the gnomon is pointing. Not the shadow, of course, because your light could be anywhere, but which way the gnomon is pointing. This one happens to lay flat, as I've gone over a long time ago, and these angles change because of that. They get narrower toward the middle, and then they widen out toward the sides. And this is, of course, 180, which is 6 a.m., 6 p.m., and the line in the middle is noon. I think it's actually this one following that. I hadn't marked any numbers on it at that time. And so you can see it's about 1 o'clock solar time, meaning according to true north and not the clock. Clocks are artificial. Their purpose is to make rapid travel more reliable, because especially that's why we have time zones, is because and universal time settings, because of rapid travel. If you weren't going very fast, very far, you wouldn't care, and local time would be fine. So on this day, it was near the solstice, the June solstice. This 1 p.m. solar time would be actually, with daylight savings time and everything in the Eastern time zone, would be about 2:40 or something like that. So it's not going to ever match completely because, as I said, the agreed upon clock time is pretty much artificial. And this being a flat type of a sundial, the angles change, but when you angle the whole sundial up, like this crude piece of wood scrap I found, and that's a paper clip straightened out, then these angles just stay at 15 degrees. They're very uniform, so you can either change the angles or of each individual or what would be a 15 degree, an hour of sun movement, or you can tip the whole thing up. Now, how far do you tip it up? You tip it up at your latitude. So that's basically what latitude is. It's the tipping angle. Whatever the cause of that angle is still up for grabs, up for dispute, but the fact is that the angles work. The latitudes and longitudes work according to how the sun appears to move. Okay? Now let me see if I can go to the one I want to go to next, which is this one. And this is the concept of azimuth. Okay? That has to do with the sun angle. What I did here is I put four compass dials basically on a grid map of the flattened out world, which, whether it's really flat or circular or spherical, is beside the point. The fact is that north is north is north. That's the point. They all point north, no matter where you are, how far south, how far north. It's going to point that way, all that way. What is that way? It's Polaris. basically. But for all practical terms, most of the time people can't see Polaris. It's during the day when they usually use this thing. So they're going to be using magnetic north. And I'm going to show a map in a minute of the difference. That the difference between magnetic north and true north is called declination. And so, and then there's also bearing, depending on which way, like a boat or a plane may be angled away from the direction it's actually moving, and that bearing is the way you're moving, even though you're, bearing or heading. I think those are interchangeable. I'm not an expert on that, but what I'm saying is sometimes, if you're in a boat or a plane, you're not always pointed at the direction you're moving. You could be off to a side a little bit and still moving in that direction because of wind or waves or whatever. So there's all sorts of terminology you got to know, but most important is the difference between true north and magnetic north. A compass is going to point magnetic north, but that varies all over the place a little bit. But for most practical purposes, it'll get you close enough. So a couple of interesting things. Of course, the way I drew this, these are 180-degree lines. A straight line is always 180 degrees. And if you add up this one and this one, you would get 360. Because if you could see, this green wedge would fit in the space of this blue circle here, and the red wedge will fit in the space of the orange circle. So this is just how you're moving along laterally or along a latitude line. That's going to affect the angle to the sun. The sun, I just happened to put at 0 of the the GMT line, and then this middle line is the equator. These two other dark lines are the tropics. Okay, and tropic again just means how far the sun can drift north or south and still go directly 90 degrees overhead in altitude when, during, on the course of a day. So this is just freezing the sun at this point, just arbitrarily. There's no big deal about having it at that point, but just freezing it at a spot during the day. If you were right under it, it would be high noon, here in this part of the ocean here, and the sun would be at, if you're standing anywhere on this line, if you're on this side, the sun is currently at 90 degrees azimuth, which is, if you take any of these dials, if you go down here, that's 90 degrees. Okay, so if you had one of these dials, I couldn't draw all of them, on this line, it would be pointing 90 degrees to the sun. Likewise, if you're on this side, it's going to be pointing 270, because that's what this mark would be, because this dial would be over here. Take this dial, move it up, and this number is 270. Okay, that's just how circles and angles and XY coordinates work. That's just how it goes. And there's nothing mysterious or nefarious about the math here. It's just very repeatable, and it just works. That's how yes, it's arbitrary that a circle is divided into 360 degrees. But there's nothing bad about that. There's nothing, powers that be about that. It's just, it works. And math is a tool like any other to describe things, or possibly to find a way to predict them. And so it works for what our purpose is today, which is explaining what azimuth is, which is just where you are on the dial. Okay, it's always going to start 0 or 360, depending on your preference, at north, which is Polaris, or in the case of a compass, magnetic north. It's going to start at 0 or 360 and then start 1, 2, 3, 4, and go around clockwise until it gets back to north. No matter where you are on the earth, that's what it's going to be. And so azimuth is what this angle is depending on where you are. Like, for example, like this one is 64 degrees. This one is 296 because you start north and you go around this way clockwise until you get to where you're pointing at the sun. This is 244 and so on. So, and what this means is if you were like here in the northern hemisphere, near the U.S., if the sun's over here, my shadow is opposite, 180 from the actual position of the sun, or at least where it appears to be, where the light is coming from, is 180 degrees away from this. Okay, so I'm actually, the shadow is going to be this one, which is 296. So if I extend this line, where the shadow is going to be on my sundial, it's going to be at 296. And here again on the sundial, the sun's over here. This is south, and the gnomon is pointing at Polaris. This is north, going this way, and this is, you know, it's an hour past high noon where I am. And the same thing over here with the angled one, this very simple shadow. This is noon. Can't see it very well, but this is 1 o'clock local solar time. So that means the sun is the opposite way, and that the angles on this drawing are where the sun is, not where the shadow is. So the shadow is 296. The shadow here is 244. You get it. So this is just what azimuth is. So if anybody uses that term azimuth, you know what it means. Wherever you go on the earth, the azimuth is so many degrees clockwise from north. That's what it means, and it's on the surface of the earth. Azimuth has to do with the surface of the earth and where the sun is in relation to where you're standing. So you would measure that angle by putting down a sundial, which would give you the opposite angle. So here again, if this is at 1 o'clock, this is 15 degrees past, or, you know, going by this one angled, 15 degrees past. And so the angle is going to be 15 degrees past 180, so it would be 195 is where the actual angle of the sun is. So you get it. These are the sun lines, and the opposite, if you extend the lines, those would be the shadow lines on your sundial, if you had one. So that's what azimuth is. It's the sun line from north going clockwise around. That's your azimuth angle. And if you go to timeanddate.com, that's what you're going to see. I think that's one of the things they list, at least on one of their pages, is the azimuth. They'll also give you altitude, which is a different issue. But I just wanted to explain what that was. Now, the difference between magnetic north and actual north, or true north Polaris, this is a map of magnetic declination. Okay, this is a flattened, distorted Earth thing, you know, but this is, if you were at any point on the ground in any of these places, regardless of the distorted shape of the continent, you would find your compass aligned along these lines. But look at that. It's crazy. I wonder, I don't have that kind of Tesla visualization capability, but to do it in my head, but you would need to try to wrap this map around various Earth shapes to see which one makes the most sense, because this just doesn't. You can tell me all day long about properties in the Earth that change it, but then that begs the question, what good is a compass if it's going to be that far off? It happens to work, just so happens to work. Oh, in Western Europe and the US, it's basically straight, but you get down to these other places, and which way are these lines going? I don't even know. This pinch point you see here is the South Pole, actually, magnetically. And everything pinches out from there, but it goes in crazy ways around here. Now, pay attention to how things are in the U.S. Fairly straight, going a little bit toward the northern pinch point, which they don't have on this map for some reason. You can see things pinching to over here. Fairly straight. The green lines, I'm not sure. I can't quite read the legend on there, but they have these green lines too. I'm not quite sure what those are, but it's almost straight up. So if you get down to like through Mexico, pretty straight. Okay, these curve way over like they're pointing toward Hawaii, is right about there. But now compare it to this map. Look how straight those lines are. But if you flatten this out, it does not match the map we were just looking at. Look at this, you know, here's the nice straight Mexico line, but here's stuff going out in the Pacific. Okay, they follow nice lines, basically longitude lines, or you can look at a top down. This is a look at from the, this is Antarctica supposedly. All the red parts are pointing away, so north, but sometimes at various angles that don't match these radial lines. And here's one looking at the North Pole looking down, and the red lines are always pointing to north. You see that? The blue ones point to the South Pole, the red ones point to the north, and so it is everywhere. So that's just one big magnet. If you had a bar magnet, which they seem to teach, as far as I can tell, with the sphere Earth model, that the Earth has a bar magnet basically on the inside. They try to explain how this works, but nobody's dug even past the mantle of the Earth, so they have no clue what's on the inside, or what, they're just guessing what could cause a magnetic field that strong inside the Earth, and oh, it must be moving molten iron or something. That's where they get that, because it has to be, because they want it to be, because this is a ball and it must have a bar magnet on the inside. Other possibilities include disk magnets or toroidal magnets, and this is something somebody else who's better at that sort of thing needs to work out, because I don't know, as far as I've been able to see, disk magnets have north on the top surface of the disk and south on the bottom surface, rather than north in the center and south on the outside as we observe with compasses. So the standard disk magnet doesn't work. I'm not sure what other magnet shapes or what these disk magnets I was looking at were made of, whether they were artificially made to have a north pole on one surface and a south on the other. I don't know. But whatever the Earth magnet is, it's a naturally occurring one, and so it's anybody's guess. All we know is what we observe on the surface, which is that these magnet bars that they've got here would work, because that's the whole purpose of a compass, so you can tell where you are, which way is north. And they're all going to magnetic north. It has to be with a compass. And they follow fairly straight longitudinal lines. But here again, if you go to, let me find the right map. Oh, come on, I know it's one of these. This one? Yeah. It doesn't add up. Like I said, out here in the Pacific, it should be pointing to the pinch point. It's doing this U thing. And I can tell you, Alaska isn't this big, and it isn't on the opposite side of this pinch. This does not make sense to me. So I'm not sure what the deal is between this map and the other one. You know, what? That's weird. How can both of these be true? This one matches observation. That's the, except this is crazy down here. Maybe that's why they don't want you to go to the South Pole. You can't find out where you're going. Because look at all these different directions that don't match any radial lines. They roughly point, you know, look at this. This red one is on the other side of that and is pointing the same direction as all the other red ones, yet it seemingly should be pointing that way. This is crazy. This makes no sense at all. This one does, that one does not on the supposed South Pole, and none of it matches this. I don't know what this map is about, whether it's maybe I've got, I mixed up and got the wrong kind of map, that it's some other thing, but I don't know. You guys can figure that out. I'm perplexed about these magnetic lines. So anyway, that's the difference between magnetic north. I think that this map makes more sense. Here's magnetic north, and here is solar north, Polaris north, true north, and that angles of the shadow on a sundial are going to be the, you know, the opposite of the sun, actually. So if your sundial's pointing at 296, the sun is at 116. That's just how it works. So the other thing I wanted to go over is, again, the movement on a given day. I've shown something like this before, but I kind of tried to tweak the picture a little bit, make it clearer. This is over one day, and the problem that has not been addressed that I'm aware of is the north-south movement of the sun on a given day. Because people will look at the tilted Earth ball lines of the equator and tropics and say that's where you get that north-south movement, but it's not. Those are east-west lines. not north-south lines. So again, to refresh memories, this is from the west looking east. This is the surface of the earth, whatever its actual shape, and you're looking at the sun coming up from the east. In order to account for the north-south movement, which is the splaying out of lines so that the sun appears where it isn't, you have to have this double lens here, a lens around the Earth's surface and a lens around the sun, to create this kind of a difference in density between the two, which is how a double concave works. It will take light coming straight down and splay it out like that. It'll be pretty straight in the middle, but it will start to splay out more as you get to the edges, which north-south, okay? This is how I'm trying to illustrate it on, again, one given day. This is, here's your east-west line. Here's east, here's west, north-south. So here's the camera looking south at the midpoint of the day, okay? That little line there is the midpoint. Here is actual and apparent position of the sun. Say the sun is going straight over you, wherever you are on the earth. This is supposedly north of, I should say, the equator. If you were south of the equator, the same thing would work, only this would be east, this would be west, that would be north, and that would be south. Works either way. You just change the names around. Anyway, we're in the north, looking south, and here's where the sun actually is, the yellow circle. This is where it appears to be. Because of the lensing, because of this. Say I'm over here in the north. The sun is farther south than it appears. Okay, this is what this means to me. I was trying to wrap my head around this. If the light is being bent north, then the sun must appear more north than it actually is. It's actually south of where I'm looking. So here's the apparent position. So if I look at sunrise, the sun seems to be north of the east. When it gets to midday, it's pretty accurate. And then when it gets to sunset, it's gone north again. That's what I observed. I observed it all last summer. And it matches dateandtime.com. And the fact is that this is that ellipse that I showed you in all those other videos in my cosmology series, which I will add this video to. Once again, I'm using OBS just to see if I can. And if it records successfully, I guess it's going to record automatically because I'm streaming through YouTube. It should save the video when I'm done. I hope it does, otherwise I'll have to do this again on a regular Hangout. Anyway, I hope I'm getting my question, I guess, across, is that because if there's a slim, if, the big if assumption, like everything else in cosmology, if this lensing holds true, then the sun can move in a very regular straight line, yet appear to go, if you're in the north, that's north of the equator, appears to go north, south, north over a course of a day. If you were in the southern hemisphere, it would be going south, north, south, that way. But the point is that there's a north-south movement on every point on Earth, at every hour, every day, that it cannot be accounted for in any other model that I'm aware of, regardless of whether it's a heliocentric spherical Earth, or a geocentric spherical Earth, or a flat Earth, and whether that flat Earth is square or round, a disc shape, as I've shown in my other videos. It does not matter. You have to have some kind of lens to account for the north-south movement of the sun at every hour, every day, every point on Earth. There's no physical way for that to happen with the sun. It can't be looping south and looping north at the same time for somebody over here. Okay, it's physically impossible. So lenses are the only way I can think of to make this observation happen. I don't care what Earth shape. This observation is true. You can go anywhere on Earth and watch the sun go, if you're north of the equator, go from north of east to south of east, or north of east to south to north of west every day, or the opposite if you're south of the equator. It will do that. Every person every day will see it. This is why you hear people say the sun is virtual or something, because it works from everybody's perspective. But it doesn't have to be virtual. It just has to be lensed. Okay, and this I think is an Occam's razor preference that I would have, at least over other imaginary, virtual, synonymous pretty much, imaginary scenarios. Because if you have a sun that's just going along in a uniform motion and yet appears to be doing something impossible, then lenses would account for that. This kind especially, a double concave. Okay, which means no matter what shape anything is, it has to have a double concave lens between the two bodies, the Earth where you're standing and whatever. And I'm not sure how this works. You know, I don't go out at night as much. I'm not sure how this works with other heavenly bodies that you see at night, such as the moon and the stars. Although you can see the moon during the day, it's rather slow and harder to see a lot of times, and so I can't get enough data to really do a good track on it. But I can with the sun, at least when we have a week or so of good weather, often enough during the summer to track it. And like I said, the tracking I've done has been enough to confirm to me that timeanddate.com is accurate in its position, its azimuth. If you just got here, I was explaining azimuth. Let's see, which I think it's on this one. Yeah, azimuth is north is north is north, no matter where you are. Your equator, tropics. This is the GMT line. There's the sun. This is where the azimuth would be. It's always clockwise from north. North is always the same direction. Clockwise from there, you go around until you find your angle to the sun, and the opposite, of course, would be the shadow on your sundial. So this is what azimuth is. If you see that term, that's a surface angle. As you're looking up at the sun, you've got a surface angle wherever you are, whatever shape this is. It doesn't matter. You can distort the bejabbers out of this map to any shape you want, and north is still going to be north, because you can stand on the ground and your magnetic compass will point a certain way, or your sundial will point a certain way, and you will still use azimuth. That's why it's a I don't want to using the term universal just means everywhere on Earth, every time of day, every day of the season, it will work. That's what azimuth is. That's why people use it for navigation. Okay, and then you have, like I've said, the magnetic declination from that. It's not always going to, the magnetic north, as depicted here, is not going to always be, and almost, I don't think it ever is, right at Polaris, where the sundial shadow is. That's why sundials don't match the clock. One of the reasons. The other is the clock are simply arbitrary, but they're within an hour and a half of each other, depending on whether you got daylight savings time, which should be abolished. Everybody petition your government to abolish daylight savings time, or summertime, whatever you call it. This map, like I said, is crazy. If this is the South Pole, supposedly this is Antarctica. Why isn't everything pointing away from the center? Why is we still have things on this side pointing like across the lines? Makes no sense at all. What's going on with the magnetic fields there? If this is accurate, I don't even know if this is a scientific paper. It says geomag.org 2008. I don't know. The one on the North Pole makes sense. Everything, all the reds are pointing north, roughly. This one makes sense. That one doesn't. And of course, this one is just crazy. I realize they're trying to make a flat map of a spherical surface, but it still doesn't. If you try to wrap that around, it's not going to match that other map with the red arrows. It just does not work, especially places like that and that. It's like, what is going on with the magnetic field there? So back to this one. So you know what azimuth is, and this is more not of altitude, because this altitude is more of a perspective thing, in my opinion, because the sun has no more reason to be said to rise and fall any more than a jet going across the sky rises and falls just because it leaves our perspective. But this north-south movement cannot be explained by perspective. It can't. There's no way. And it would not loop back like this, I don't think. Maybe I'm wrong. I don't know. But I don't think perspective accounts for the north-south movement of the sun on a day, and that it's consistent for every, if you keep extending this lens forever in every direction, both, east and west, the sun is going to go across like this, and it's still at every person, every longitude line along that way, every hour, it's going to do this. Like the sun is appearing to do this as it goes across the world. Okay? It can't be, it's not doing that. The sun is not doing that. It's moving in somewhat a straight line or a very big arc, we can't tell, but for all practical purposes, for any observer on the ground, where it's represented by this camera, it's doing this at every point. Every camera, no matter where you put it, east or west of here, is going to see the same loop on a given day. The same sine wave is not even really a sine wave because it never goes negative that far. But summer solstice in the northern hemisphere, so-called, this is north of east, and it will go to about 70 degrees altitude, and my sundial is always going to have a shadow on it because I'm north of the Tropic of Cancer. Therefore, the sundial will always have a shadow, which means the sun is not 90 degrees overhead. So here again, not perspective as far as its altitude goes. Altitude is simply how far above the Earth it is, and that is an unanswerable question because there are too many variables in the equation. If you don't know the size of the sun or the distance, then you can't figure out the other one. You have to assume one or measure one. If you know the size, you can figure out the distance. If you know the distance, you can figure out the size. It's simple algebra. But we don't know either. It's all arbitrary based on those stupid imaginary experiments from the past they tell us about, like Eratosthenes, which has too many holes in it to bother with anymore. But the fact is, you can get a sundial and prove to yourself that the sun is not directly overhead, like I did also before I had a sundial, and I noticed with my scope that has fairly accurate degree markings on it, that when it looked like on the solstice the sun was directly overhead, of course it wasn't. There were shadows, and the scope read about 74 degrees. So vertically 74 degrees. It's not the azimuth, it's the altitude. So forget azimuth when you're doing how high is the sun, that's the altitude. And if you're outside of the tropics, it will never reach 90 degrees, ever. But it will go farther north than it should. So here I am. See, even at the southern solstice, which we're approaching, southern winter solstice, which we're approaching, the December solstice, the sun still does a little bit of loop. It's not very obvious because it's so far south. But how can it be doing that? How can it be even at the solstice, June solstice, okay, the sun is as far north as it's going to get, and it's still, I'm north of the tropics. It should never be farther north. It should be a little bit south of east. In other words, if this is the east-west line, the sun should never quite look directly east from where I'm standing up here. It should never be 90 degrees. If you go look at the let me get the these again. Here's 90 degrees, okay? If I'm right here, roughly, say this is up here in the U.S., 90 degrees would be the summer solstice. You would think the farthest north it could be. Actually, it's going to be, if this is 90 on this line and I'm farther north, then it should be down this way a little bit, like less than that probably. But it should never be 90 degrees, right? If it rises in the east, it should, because it's this far south, or actually it's on this line, remember, we're doing the June solstice, and I'm up here a little bit, this is not that line, okay? It's never going to be this line. It's going to be like down like this, okay? From here to here is not 90 degrees. It's going to be like 100 or so, okay? But what did I observe on the June solstice? The sun is up here. That is to say, farther away from the equator than it actually could be. That's why I go back to this lensing. What else could explain it but an apparent position, not an actual, but an apparent position that puts it farther north than it can possibly be? Because we observe on the ground, that's why we have tropics, that there's a certain point north and south of the equator where the sun will, on a solstice, be 90 degrees overhead, vertically, of course, and places outside of the tropics never see that. The sun is never 90 degrees overhead. That's how the tropics are defined. And so how is it possible outside the tropics for the sun to be less than 90 degrees in the east or west? I can't think of any physical way to make all these things work than the double concave lens, and I'm hoping that this apparent position as opposed to actual is illustrating what lenses do to light. Now, we also have to figure that this needs to also account for the heat of the sun. It isn't just the light that gets bent. Heat can also get bent, I think. I haven't done experiments with heat like I have with light, but there are anomalies with the sun's heat. For example, noon isn't necessarily the hottest time of day. Usually it's afternoon that the temperature is the highest, at least where I live. Your mileage may vary, as the saying goes, but the thing is that this is something we have to account for, not just light but heat when it comes to the sun. Also, the seasonal lag between light and heat. You would think intuitively that the warmest time of the year would be approaching the June solstice in the northern latitudes, and that it would start to get cooler when the sun started to go past the solstice, but it doesn't. It gets hotter. So the hottest months of the year in the northern hemisphere are the months beginning with the solstice and going to the equinox. That's the hottest time of year. But it's not when the sun is farthest north in its appearance. So go figure why there's a seasonal lag in the heat compared to the light of the sun. And then we have a daily lag in the sun's heat. And I don't know what to think about that, but it's a problem that needs to be addressed in any model. Here again, I don't care what shape of Earth you pick. You have to deal with the sun's motion. And also, of course, as I've done on other videos, we have the clock motion to deal with too. The rotation. So I'm hoping this all recorded. Okay, good. In the chat, they said it did. And I'm trying to get my watch page. It says video output low. Sorry if I'm lagging. I don't know what's going on, but I think I'm going to go ahead and end the broadcast. I hope you guys can hear me. Let me type in the chat. Can you all hear and see what I'm saying? Because I can't tell. It says 6 people watching and the video output is low. I don't know why it's low. It started off fine. It does this to me all the time. I don't know. I hope it hasn't been frozen. But also, it should record all of this, so it'll catch up eventually. Anyway, I'm going to end the broadcast. Anyway, as I'm typing in chat. And, yeah, with 6 people, I don't know. But anyway, this is a problem that we need to deal with in any Earth model, including the standard one. They don't account for this motion. And here again, you can't use the tilt of the Earth to account for it because the tilt only accounts for the seasons. And the latitude lines only account for east-west motion, not north-south motion. Okay, thanks in the chat. Yeah, I wasn't sure. It tells me video output low, and that's all I know. Okay, good. All right, well, oh, I see I'm buffering. It seemed to have buffered just then. So I think that's it, and I don't know if I'll try. I wish I could figure out this poor audio output issue with Hangouts. I don't know what the problem is. I am using Linux, and whatever, I have trouble finding browsers from one update to the next that even works with Hangouts. So it's like playing whack-a-mole with browsers. One time, one update, Firefox is working. Well, that stopped because they don't do plugins. And then the next one, Chrome. Then the next one, Chromium. Something breaks every time, and it's just irritating. But I don't do Windows. I'm not doing Windows, and Macs are too expensive. So here I am. All right. Well, we're buffering again. Um, I'm going to end the broadcast, and probably the next hangout I do here will be a Bible one. I'm not sure what yet. I don't know. Might do another science one if I figure anything out. And thanks again for coming. I think I got to go. Okay. I just wanted to do this thing I've seen people do where they restart a broadcast. I want to see if it makes a different video or not. Um, if it does, this is just, I don't know if it's going to or not. Hey, you're quite welcome in the chat. Thanks for coming. I was just trying, since I'm using OBS today, I thought I'd try to restart it and see what happens. Okay, well, we'll see what happens. I noticed also I cannot uncheck DVR when I'm using OBS, so that probably contributes to buffering. I don't know why it won't let me uncheck DVR. Oh well. Alright. If this puts up a second video, I'll delete that one.